second hour. And in this hour, starting this right now, we are going to talk about the first topic, that is to sample a signal. Sample being a verb, okay, to sample a signal. To sample a signal from discrete time, from continuous time to discrete time. Okay, so we talk about discrete time sampling of continuous signals. So there, we'll talk about two topics, all right? So first, we'll tell you the definition of sampling in the time domain. It happens in time, all right? Everything happens in time. But then we talk about the effect of the equivalent effect that created. This action of sampling creates some effect in the frequency domain. And we talk about that. Yeah. So sampling in the time domain, first thing first, let's look at this diagram, this very simple diagram, okay? Let's look at the diagram. So on the left, we have a signal, okay, as a function of time, t being the time, and the unit might be second, okay. Time happens continuously, and let's denote a continuous time signal as x sub c, okay, x sub c. C stands for continuous, okay, C stands for continuous. And then we have this box that we denote as C/D, C to D conversion, okay? Continuous to discrete conversion. Okay? Continuous time before and discrete time after the conversion. And with that, in this, we need to specify a sampling period that's denoted as T, okay, sampling period T. So the key idea is really just this equation, okay? There's one equation right there, x. Now we look at the continuous time signal at nt, right? N is 1, 2, 3, 4, 5, okay? And t is a constant. The sampling period is a constant, okay? For example, 125 microsecond or something like that. T is a constant. Right? T is a constant. So what this equation means is that we will look at our signal. We look at our signal at integer multiple of t, 1t, 2t, 3t, and so on. And also in the, time can go backward, 0t minus 1t minus 2t. Integer multiple, 整数倍数的, integer multiple of the sampling period t. So that's the moment we look at our signal. And then we look at the signal quickly and we record the result and call them x of n as a sequence of numbers. Sequence of numbers, right? 数列. The result of discrete time sampling is a sequence of number denoted as x of n. So far so good? So that's the notation. So this is a system diagram of continuous to discrete time conversion, C to D. T being the sampling period, n is integers, right? N is an integer. And I have one remark, okay? So this course is called what? What's the name of this course? What processing? Digital signal processing, right? But somehow here we cannot yet, I say that x of n, this signal, discrete time for sure, cannot yet be called digital. Not a digital signal yet, okay? And the reason is because x is still a real number, any real number, which might be irrational, 无理数, right? So we know that a computer, when we use a computer to store and process a number, the number has to be represented binarily. 要有二进位, binary. You need to use some kind of binary representation system to decode, to encode our number. And that hasn't happened yet. So this is just about sampling, measuring the signal, taking a measurement of a signal at this moment, at every integer multiple sampling period. Okay, so not yet digital. We do not represent the numbers binarily in a binary representation yet. Okay, so by definition, this is not yet digital, but we will come back to that. We will come back to this topic when we discuss quantization. That's how we round up our number, and so that the number is ready to be stored and processed by computers, okay? We'll come back to this topic. But in the next hour, we'll just stick with this discrete time notation, and we think of a discrete time signal as a sequence of numbers, okay? Sequence of numbers with an index n being integer. So now we have a question. But let me, before I ask the question, let me just draw, let's try to make a sketch of what's going on, right? Let's make a sketch. Suppose that we do have a signal like that in the time, okay? And this is our time axis, happens forward. And this is a continuous time signal that we denote as x sub c of t. So sampling really means that we are going to measure our signal at integer multiple of the sampling period, 0, 1t, 2t, 3t, and so on. So here, like the spacing in between points is the sampling period, okay? Which, for example, as I said, might be 125 microsecond, something like that, a sampling period. So as a result of sampling, we are going to look at our signal right here. It's so high. We may even have a vertical axis, right? Any continuous time signal may have a unit. The unit might be, let's say, millivolt, right? The unit might be millivolt or any other physical quantity. So we take a look at our signal at 0t, and then again at 1t, and again at 2t, and 3t, and so on, and so forth. Yeah. So that's the idea, kind of a sketch of what's going on when we convert a signal from continuous time to discrete time. Okay, continuous time 连续, discrete time 离散. So that's a sketch. But now then, let me ask a question. Let's ask the question together. We need to wonder if C to D being a conversion, if the conversion, whether or not the conversion is invertible. 是可逆的吗? Is the conversion invertible? That's being said, what we mean is that when we convert the continuous time signal to a sequence of number, can the process go back? Can we reconstruct the signal out of its samples? If what we know is all about only discrete time samples, can we synthesize the signal back in the continuous time? That's the question. Is C to D conversion, is it invertible? Is this process invertible? Does the inverse exist? Does the inverse exist? Okay. Because this is an important question, because if it exists, then we can have a D to C conversion, right? C to D, and we can very well call the inverse D to C, right? C to D first, and then D to C, right? But really, is any signal, is a sampling of a signal invertible? And the general answer is no. The general answer is no. C to D conversion, continuous to discrete time conversion, is generally not invertible because of an effect called aliasing, right? So I'm going to explain to you. So that is to say that it is possible that we have two different signals, x1 not equal to x2, okay? It's possible to have two different signals that become identical, 变成一样啊. They can become identical after sampling, in that at every moment nt, the equality happens to hold. It's possible, right? It's possible for any integer multiple of t. Okay, it is possible that in this signal we have these samples at nt, but you may as well have another signal. It's possible that we have another signal that happens to equal to our signal at every moment of nt, but in fact they are different. So what do I mean? So it's possible to have another signal that happens to go through this point and then deviate and then go through this point again and then making its detour and go crazy, and as long as it's a continuous time function, right? It's possible to encounter such situation theoretically, right? So this is just to explain to you that it's possible that we have two different signals that become identical, 变成一样, become identical after sampling, right? Theoretically, it's possible, right? So theoretically, mathematically speaking, C to D conversion is not invertible in the most general sense. It's a many-to-one mapping, right? As a function, right? It's a many-to-one mapping. So that's an important concept. And here is another plot, okay? Another example, a kind of a good example for aliasing. So let's say we have the red. The red line is a periodic signal, a sine wave, if you will. So that it happens, it just goes up and down all the time, right? And let's say we are going to sample this signal with a t of something. T of 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. It looks like my t, my sampling period is 1/8, 1/8嘛啊. So in this example, we have, in that example, we have t equals to 1/8, if you will. And the result is marked as circles, okay? The circles tells you the result of sampling with this sampling period. So first, it crosses right here, and the next moment, next moment, next moment, and so on and so forth, okay? So is this a valid action of sampling? Is it valid? Sure, of course it's valid. We are going to measure our signal every so often, every integer multiple of the sampling period, which is 1/8, okay? So of course this is a sampling, there's nothing wrong in here, But what is wrong is that if you just pretend that you don't see the red, okay? Let's pretend that we only see the result of sampling, which are the circles, right? What can you tell? If you only look at the circles, are you going to think that the underlying signal is the red one, which has a much higher frequency, at least appearing to by inspection, 用看的, By eyeballing this example, will you say that, okay, I'm looking at the circles, and the underlying the signal, the corresponding continuous time signal must be this red one? It's not so likely, It's not the most natural way to look at your result of sampling and say and conclude, 下一个这样结论, and conclude that, well, our signal in analog is the red one, which fluctuates at a much higher frequency. Okay. Instead, what is more natural? Okay, anybody tell me what is more natural? Of course, this is like roughly speaking. Okay. The more natural way to look at the circle is to interpret it as a result of sampling a signal that varies more slowly, like that. Right? That's a more natural interpretation. Okay, that's more natural. So this is just to tell you that two different signals. This red one as well as the one that I'm drawing right now, as well as this one, these two different signals can happen to share the same result after sampling. Okay, so there's ambiguity. There's ambiguity in looking at the result of sampling. In the most general sense, sampling is not invertible. Okay, sampling in the most general sense is not invertible. And this ambiguity is what we call aliasing. Okay, sometimes a high frequency, we come back to that. When sometimes a high frequency component can disguise itself. Okay, 伪装, can be disguised as a low frequency signal after sampling. Okay, so there's ambiguity in that. So far so good? Yeah, aliasing. Typically, aliasing is something to avoid, and we will talk about that. Okay, we don't want this to happen. So, but unfortunately, if it happens, then there's no way we can tell whether the signal is high frequency or low frequency after sampling. There is ambiguity. So the next better thing that we can possibly assume is that, however, we step back and require the signal to have this property. What property? If we require our signal to be band limited, okay? So in this handout, every time I introduce a new terminology, I use italic. 我用斜体 Every time you see an italic word, that's a new terminology. So this is to step, so if we step back and require our signal to be band limited, that being said, that means if the bandwidth of the signal is finite, then turns out that it becomes possible. It becomes possible to reconstruct the signal from its samples. It becomes possible to reconstruct the continuous time signal from the result of sampling if we assume that the signal is band limited, if the signal has a finite bandwidth in the frequency domain, okay? If that assumption can be made, then it is possible, it becomes possible, roughly speaking, to reconstruct, to make the reconstruction from its discrete time samples. And just jumping to conclusion, directly, we say that we require the sampling, and how can we make sure this happens? We will require the sample. We need to require the sampling frequency. Sampling frequency is defined as 1 divided by t, 1 over t. Okay, 1 over t. So as an example, if t is again 125 microsecond, I mean, then f under this definition, that's a definition of sampling rate. F sub S stands for sampling, okay? Sampling frequency or sampling rate being 1 over t. So if we do a quick calculation, then the result is what? 8 kilohertz, if I understand correctly, something like that. Okay, sampling frequency has a unit of hertz, right? Sampling time, sampling frequency. So just long story short, roughly speaking, the conclusion turns out to be that we should require the sampling frequency to be higher than 2 times the bandwidth of our signal. You're interested in a signal which has a bandwidth of B. Make your sampling frequency at least 2 times higher. So that's a recommendation. That's kind of a universal recommendation. Yeah. Jumping to a conclusion first. But why that's the case, we will go through the derivation next, okay? But that's the conclusion, sampling rate. We recommend it to be set at least 2 times higher than the bandwidth, 2 times broader. Yeah. So far so good? Yeah. So that's just to summarize. Now we have introduced a time domain definition of sampling, which is we have a continuous time signal. We go through a C to D converter, and the result is x of n, and with a sampling rate, sampling period t, and just please memorize that xn is defined as x of c, the continuous time signal sampled as integer multiple of t. That's a definition. That's a sort of a definition. Okay. So that's what's happening in the time domain. But next, let's talk about the effect in the frequency domain, right? Yeah. Talk about the effects in the frequency domain. And now we need to introduce a few variables, okay? So let's first define kind of a strange thing that I denote as S, right? We'll come to that, yeah. So let's make a few definitions. Let's first define S like that, being a summation from -infinity to infinity delta function, okay? Delta function shifted to the right or to the left by integer multiple of t, okay? And we sum them up. So let me draw a picture, yeah. If you have your iPad, you can also write on the note. So the room is supposed to be left blank here for you to take notes. Okay. So let's make a sketch. S of t. What does S of t look like? It's a summation of delta function, right? Okay. So we know that delta function is typically sketched as using an arrow pointing up, right? An arrow pointing up representing a delta function. This is delta t, being infinity at time 0, right? Delta t is defined as being infinity at time 0 and 0 elsewhere. Just to review, such that you take the integral of delta t with respect to time, then you get unity. Okay, that's a definition. That's sort of that is what delta t represents. Yeah, it's a generalized function. All right, so we have delta t, but that's just one component. We have an infinite series of delta t shifted to the right and to the left, right? So to draw a picture of S of t as a summation, you can imagine that you have, okay, this is delta, another delta impulse at t, and yet another one at 2t, and so on, right? So that's what we mean by summing up a sequence of impulse, an infinite sequence of impulses at integer multiple of t. Let me just extend my drawing for a little more, give you a little more, a few more spikes right here. Okay, minus 2t, minus 3t, and the spike train extends to on both sides to infinity. A train of spikes, if you will, spikes, 知道吗 ？spikes 啊，刺刺的东西 spikes 啊。All right, so it's a train of spikes denoted as a summation of delta functions, shifted to the right and to the left. So this is S of t. And then we also define something like this. We define the product. Just multiply our signal with S of t, and the result will be denoted as X sub S. Okay, X sub S. Yeah. So what does that mean? Knowing that delta t has this definition like spikes, so what we are going to do is to consider now, well, if S of t is like that, and if our signal is like this, let's say this is our signal, okay? So let's say this is our signal, and the signal is denoted as xc, right? Our continuous time signal, everything is still in continuous time, conceptually, right? So now, everything is still in continuous time, and we are going to multiply the two of them. We multiply our signal with the spike train, okay? With a train of spikes. What will happen? What will happen? So the result, at least in the time domain, is going to be change of height, change of the height of the spike, okay? We're going to change the length of a spike by our waveform, okay? So result, naturally, I hope it makes sense, will be a spike, but at a height that is modulated by the amplitude of our signal. So the result is going to be like this. And we just conceptually, we say that everything is still in the time domain, in the continuous time domain. Yeah. Okay? Can we agree on this? So this is a sketch of the result of multiplying the two of them. Okay? So X of C, our signal being in white, the white line is our signal originally. And now the yellow one, also a train of spikes, but each with different height, 高度不一样, but each with different height, and possibly also the polarity, 极性也不一样, each changing its polarity and height according to the amplitude of our signal. So that's a result of multiplying our signal with the S of t. Okay? And we're going to denote this result as X sub S. And why do we do that? Okay, so I said in this slide, we are going to, this is a preparation to explain the effect of sampling the frequency domain. So as a step for preparation, we introduce this definition, X sub S of t. And the reason is because we argue this train of spikes with change in amplitude and polarity, it is a representation of sampling, right? If you look on the right, what is sampling? What's going on for sampling? Sampling is to take a measurement of our signal, and now the result is a train of spikes, if you will, each with different height, right? And possibly also changing polarity. If this goes negative, right, the polarity will change over there. But basically, we are modulating the height of a train of spikes by the amplitude of our signal. That's what's happening. That's another interpretation for sampling, right? So we argue that this is exactly identical. The only difference is that we draw an arrow. The only difference really is we draw arrows instead of, if you will, circles over here. Here we draw dots. We draw dots over here, fill circle, if you will. But then over there we draw arrows. 就画箭头. But otherwise the two are equivalent. Can we agree on that? This and that. Just the action of sampling, by definition, is the same as multiplying our signal with a train of spikes, a train of delta functions shifted to the right, to the left. Then we modulate the amplitude accordingly. Okay, so they are equivalent. But it turns out that it's more convenient to discuss the Fourier transform using this notation. Okay, so that's why this is how we prepare for a discussion. Okay, now we are prepared. Now we are prepared for the discussion of what's going to happen in the frequency domain. Is that clear? Yeah. So next thing, so if you agree with me that these two are equivalent to different interpretations, then we can now review the definition of Fourier transform for continuous time signals. Okay, the Fourier transform in this textbook has this notation. Okay, if any signal x, when we transform the signal and we denote the transform by script 草写 by script f 草写的 f, the Fourier transform of our signal is a spectrum in the frequency domain. And the notation, let me introduce slowly. The notation is that they are going to form a Fourier transform pair, small x, big X. Is that clear? In this course, we use small x, we use lowercase letters, 小写的 we use lowercase letters for time domain signals, and uppercase for frequency domain. Okay, small x for time, big X for frequency, and we also use big omega for the frequency variable. Then with this, then the definition, mathematical definition for a transform is listed on the right. So here is written on the right. We are going to multiply our signal with e to the minus j omega t. Multiply them and then take an integral. The result is a function of omega. Is that clear? Yeah, so I hope this sounds familiar to you, brings you back some memory. If you have taken signal and systems. Okay? And the integral runs from minus infinity to infinity for continuous time Fourier transform. Okay, so any question regarding the definition of Fourier transform and the notation? The notation, right. All right, so just to make sure that we are on the same, we have the same notations. Here, j is square root of -1. J is I. Okay. Somehow in EE department, we use j more than we use I. Okay, so in this course, we use j for square root of -1. And e to the j theta, now you should be familiar that is e equals to cosine theta plus j sine theta. And here we have big omega denoting the frequency variable. And what's the unit? The unit of big omega, strictly speaking, is radian per second. A radian per second. If it appears in the power right here, 在指数的地方 it appears in the power right there. So e to the j omega t is going to be periodic, right? The frequency is exactly omega divided by 2 pi. That's the frequency. And the frequency unit will be hertz. Okay, so just to make sure that everything agrees with everything else, that's the notation we're going to use. Also your unit, okay, for you to pay attention. So with that, we call the result a spectrum. Okay, so I call X, this big X, the spectrum of our signal X of t. Big X, the spectrum, small x, the signal. Okay, so everybody okay with the notation? Yeah, maybe, yeah. So hope that that's okay. But let me just write down the copy this notation in case we need it. Okay, f of x of t is gonna be denoted as big X with variable j omega, and the definition really is to take the integration from minus infinity to infinity, x of t inner product with that, and taking the integral, the t becomes a dummy variable, and the result is a function of big omega. Yeah. All right, so that's a bit about the equivalence of sampling as if we are multiplying our signal with a spike train, and also introduction, a review on the notation and definition of Fourier transform and what's going to be happening next. Next, we are going to discuss what's going on when we do this action, okay? When we define sampling as if we are multiplying our signal with the train of spikes. This is a multiplication in the time domain. But then the question is, what will happen in the frequency domain? Okay? What will happen in the frequency domain? Xc has a spectrum we are going to denote as big Xc. Okay? That's a notation. And if you will, S of t will have a spectrum that we can denote as big S of in the frequency domain. So in the next slide, we are going to go slowly, okay? Hopefully we can finish this derivation. So we are going to see what's going on when we multiply these two signals in the time domain. And then take the Fourier transform, right? And then take the Fourier transform. I think I can probably erase things over there. Okay, so but take a look. So this equation derivation could be quite tricky. So let me first take you through. There are only like 5 equalities, right? 只有5个等式嘛. Yeah. The first thing first. So recall that S is a train of spikes, summation being summed over the dummy index of n. Okay. And just let me also mention slowly that whenever we have a summation, if I do not specify the range of summation, that means by default we are going to sum up from minus infinity to infinity. Okay, that's my notation. Okay, to be sort of sloppy. So using sloppy. Allow me to be sloppy whenever the range is not indicated. That means summation from minus infinity to infinity. Okay. So here we have S of t as a spike train, and it turns out that, okay, somewhat surprisingly, if you have an encounter, this is a somewhat surprising result that it's Fourier transform. The Fourier transform of this signal looks like itself. Okay, the result is also a summation of spikes in the frequency, now in the frequency domain. Now in the frequency domain, what's going on here? So that means if S has a spacing, S being the spike train in the time domain with a spacing of t, then when we go to the frequency domain, it looks like itself, it resembles itself, but the spacing is now becomes inversely proportional. The spacing in the frequency domain is going to be 2 pi divided by t. That's the spacing. And now the dummy variable is denoted as k. Okay, we're going to sum up spikes in the frequency domain. The result is a spectrum. Okay, it's a Fourier transform of our spike train in the time domain. Right, the result is a spectrum, but it has this expression. It's a summation of impulses in the frequency domain. Somewhat surprising result, okay? But now the spacing is inversely proportional to t, okay? So let's try to draw a picture right here. So now, after Fourier transform, now things are in the frequency domain, big omega, right? But now the spacing, we have the DC at frequency 0 for sure. But then with the spacing equaling 2 pi divided by t, we have the next spike on the right. We have the next spike on the left with also the same spacing, okay? Same spacing, going to negative frequency and positive frequency, okay? That's how Fourier transform works. So the spacing becomes inversely proportional with, so if we denote this as omega s, then this is 2 times the sort of the spacing. Yeah. So we define 2 pi over t. We define the spacing as big omega with this notation, this variable. Then now again, the result of Fourier transforming the spikes, the train spikes, the result looks like itself. Only the spacing becomes inversely proportional. The more densely they are populated in the time domain, the more the broader they are apart. The more narrowly they're together in one domain, the more apart, more separated apart they are in the other domain. Inverse proportion. Okay, inversely the spacing becomes inversely proportional. So that's the first thing to notice. And secondly, you need a sort of a normalization factor over there. So that's not super important. So I'm just going to, please trust me that we have this normalization factor right there. Okay. So this is one of the only few functions which preserves its shape after Fourier transform. I don't know if you have heard about this. There are only few functions that preserve its shape. 形状保持一致啊, preserves its shape after Fourier transform. This is one example. The other is Gaussian function. Okay, good student, right? Yeah, so kind of a good thing to know. But turns out that we are not going to, I am not going to use this directly. Okay, it's kind of cool to know, but if you will, so if you now look at this result, what we call big S, the spectrum, is a sum of spikes, right? But we also know what? What we know about spike what do we know about one spike? Every one spike in the frequency domain. What does it represent? Every one spike in the frequency domain represents a periodic signal, which can be written as e to the something t, something being its frequency, right? So just quickly, if the spectrum, if the Fourier transform is a sequence, an infinite sequence of spikes, then we know that back in the time domain, the signal can also be represented as a sum of complex exponentials, periodic signals. Every exponential j, this is the frequency, k times 2 pi divided by t. K times 2 pi divided by t is right there. That's the correspondence. Okay? Every one component right here corresponds to one term in this summation. Now we are going back to the time domain. And this is quite tricky. This is a tricky part. This is really the tricky part. Okay, that I'm suggesting, okay, this is a suggestion, okay. I'm suggesting that you accept the equality holds. And this is quite tricky. Why? Because S is, we have already written the expression for S, right? S is nothing but this. But now I'm suggesting that maybe, yeah, I'm trying to convince you. I'm trying to convince you that S of t can also be represented in terms of its Fourier series in time domain. Because each one of these terms, each one corresponds to one delta spike in the frequency domain. And I agree that I apologize. No, I acknowledge that this is a tricky part. that we are going to rewrite and use this expression. We are going to rewrite S of t, which is defined like that, as a sum of its Fourier series. This is Fourier series expansion, if you will. And that's the tricky part, okay? I think that's a really, really tricky part. Let me stop for a while, okay? Any comment? Yeah. Is anything that's not clear? Is everything clear? It's quite tricky. This equation is really the tricky part. It's also problematic. It is also problematic, but just bear with me. We are going to assume to be using this equality. Okay? We're going to be using this identity, 这个恒等式, which might be problematic, but anyway, that's what I'm going to use next. Okay, All right, so yeah. So now, after I mentioned that this is a tricky part, just pretend that for time being, for a moment, we agree that this is real. This is true. Okay. For the moment, let's agree that this equality holds, and this is a good consequence. The consequence is that now we are able to talk about a Fourier transform of this guy right here. So this thing here is the result of multiplying our signal of interest. We're interested in knowing about this signal. So we multiply it with the spike train in the time domain, and then take the Fourier transform, right? But now the spike train can be rewritten as that. So why not just plug in this? Let's just substitute this expression into here, right? Fairly straightforward, right? We are going to substitute this expression in here. And we know that Fourier transform, everything's linear, so we can take the summation from the inside to the outside of Fourier transform. You can do that. Fourier transform is linear, a linear operation, linear transformation, right? So take the summation outside as well as this scaling factor, which is not super important. Okay, take them out. Now in the inside, we have a summation of Fourier transforms. We have a summation of spectrums, if you will. And now, how about each term right here? We are going to sum over the index k. And each term now in the time domain, still in the time domain, each term has an expression of our signal multiplied or modulated with a periodic signal of frequency k times 2 pi divided by t, if you will, right? Because this is a frequency, right? This is sort of a modulation frequency. So far, so good? Just linearity of Fourier transform. Right? So the second equality here is just linearity. Linearity of Fourier transform, right? Fairly simple, you can figure that out. But then the interesting thing here is that what's going on here? When we multiply a signal, when we modulate a signal with a carrier, using the terminology of in communication, when we multiply our signal in time with this complex periodic signal, complex exponential, if you will, then what's going to happen in the frequency domain? The spectrum will shift. This is the time that the moment that we can apply the shift theorem in Fourier transform. Okay, we multiply a signal. So this second equality, equation 2 right here, is equation 3 right here. The equality right here at the bottom is a result of the shift theorem. The shift theorem. So each of the term, the summation is still there, but each of the term is a result of multiplying our signal in time with complex exponential, which is periodic, right? So we're going to shift the spectrum, entire spectrum of x to the right by so much, by k times this frequency, 2 pi divided by t. So that's a result of the shift theorem. So if you take note, shift theorem, that to say whenever we have a signal and we multiply it with a e to the j something, let's say omega naught t, a constant frequency, right? and you take the Fourier transform. The result is x, but shifted to the right by so much. Okay, the spectrum is going to shift to the right or to the left depending on the sign of the carrier frequency. That's a shift theorem of Fourier transform. Okay, now. All right, so that's a very brief derivation of what's going on when we multiply our signal with the spikes in the time domain. Yeah, over there. Over here. Multiplication in the time domain. It turns out that the spike train has a different expression which allows us to use the shift theorem to reach this conclusion that the spectrum of that. The spectrum is going to be a result of the original spectrum shifted to the right and to the left infinitely. There's going to be infinitely many copies of the spectrum, each shifting to an amount. In the frequency domain, we're going to sum them up. They all add together. They're all superposed. And again, this factor is not so important. Okay, the important thing is that they all add up. All the components are going to add up. Okay, so I think I can stop right here. So tomorrow when we come back, let's make a sketch. Okay, let's continue this discussion of what's going on when we sample in the time domain. Okay, and the result is that in the frequency domain we have a few components, infinitely many components that add up. Okay, so tomorrow when we meet, we start with a sketch of what's going on. All right, so that's it for now. Thanks for sticking with me. See you tomorrow.